ZK-Rollups do not automatically make transactions private. The zero-knowledge proof usually shows that the rollup updated state correctly. Hiding users, amounts, or activity requires additional privacy design on top. So far, we've looked at scaling, ZK rollup mechanics, and privacy on public blockchains. Now we connect those ideas. ZK proofs can verify correctness, but privacy depends on extra design choices, especially when compliance and responsible disclosure are part of the system. The main misconception is treating zero knowledge as another word for privacy. In most rollups, ZK means a validity proof. Ethereum can confirm that a batch was processed correctly without rerunning every transaction. But the rollup may still reveal senders, recipients, amounts, apps, or timing data. Privacy is not automatic. It has to be built into the protocol. This distinction matters because rollups often publish transaction data for data availability. That public data lets users rebuild the rollup state and exit if an operator fails. The proof shows that the state transition followed the rules, but the published data may still expose activity. Validity, scalability, and confidentiality are separate design choices. A ZK rollup sends Ethereum two very different kinds of information. First, it submits a validity proof, which checks that the new state was computed correctly. Second, it may publish availability data, such as compressed transactions, state diffs, addresses, call data, or app-specific fields. That data supports reconstruction and auditability, but it can also reveal user behavior. Compression reduces size. It does not create privacy. Rollups publish data for a security reason. If users can access the data, they can recompute balances, check the operator's claims, and recover state if something goes wrong. That is what makes exits and censorship resistance credible. Privacy pushes in the other direction. Less visible data means better confidentiality. The design challenge is to hide sensitive details without hiding the evidence users need to verify, recover, and safely leave. Privacy is not only about hiding the amount or the recipient. Every transaction leaves surrounding clues. Timing can reveal payroll cycles, trading routines, or personal habits. Size and frequency can distinguish casual users from bots, funds, or businesses. Counterparties can expose social and commercial relationships. Observers do not need one perfect secret to break privacy. They can combine many small signals into a surprisingly accurate profile. Timing is one of the clearest examples. A trade right after market news may suggest intent. A payment on the first of every month can look like payroll, rent, or a subscription. Wallets that move together may appear coordinated. For this reason, privacy designs often use batching, delays, or encrypted mempools to blur timing signals. Other fingerprints can be just as revealing. Even when values are hidden, observers can compare transaction size, gas usage, contract calls, timing, and repetition. A swap, an NFT purchase, a bridge transfer, and a game action each leave different patterns. Over time, those patterns can reveal habits, preferences, and sometimes strategy. Strong application privacy protects the whole journey, not just the final balance or amount. On public blockchains, observability can become identity. When funds move through a bridge, analysts may link the Layer 1 source to the rollup wallet. Reusing addresses makes that link stronger over time. Exchanges, KYC services, and recognizable smart contracts add more context. Real privacy therefore depends on wallet separation, account abstraction, careful bridging paths, and habits that avoid creating an obvious behavioral fingerprint. Building a private rollup requires more than valid state transitions. The system must hide transaction details, break obvious links between users and actions, protect pending transactions before inclusion, and support selective compliance proofs. That usually combines ZK proofs with encryption, commitments, nullifiers, and shielded state. Each layer reduces disclosure, but adds cost and complexity. A strong design preserves privacy without weakening security, data availability, or fund recovery. Pending transactions create another privacy risk. In a public mempool, trades expose intent before execution, giving searchers time to front-run, copy, or infer strategy. An encrypted mempool changes that sequence. The user submits ciphertext, The sequencer orders what it cannot read, and details are revealed only after ordering is fixed. Designs may use threshold encryption, trusted execution environments, or commit reveal patterns. This reduces pre-execution leakage, while post-execution data still needs separate protection. Private balance systems use a different pattern. Instead of showing everyone's coins on the ledger, a deposit can become a commitment, a locked cryptographic note that hides the value and owner while still supporting validity checks. When the note is spent, the user reveals a nullifier, proving it has not been used before without linking directly back to the deposit. The larger and more active the shielded pool, the stronger the privacy, assuming users manage keys and behavior carefully. Account abstraction can make privacy feel normal instead of fragile. Smart accounts can rotate keys, set permissions, and separate identities across workflows. Sponsored transactions can hide direct gas payment links, although the paymaster may still learn metadata, so trust assumptions matter. Session keys reduce exposure by limiting what an app can do and for how long. The design principle is simple. Make the private path the default path, because bridges, signatures, recovery, and app behavior can silently reconnect identities. The key lesson is that zero-knowledge validity proofs scale execution, but they do not guarantee privacy. Published transaction data and metadata can still expose users. Privacy requires deliberate architecture, including encrypted mempools, shielded state, private balances, and account abstraction. Next, we'll connect these design choices to responsible compliance and adoption.